Here's a rather interesting conservation momentum problem. This problem's about the following. You have a dart down here. This is my version of a dart here with a sharp pointy thing on it, which is going to be launched straight up at 9 meters per second squared. So that's the acceleration that it's going to have. Now, 3 meters above the dart is a cork. That's just going to be dropped straight onto the dart. So what will happen is the dart's going to go up, the cork's going to go down, the two are going to stick into each other. And what they like to know then after this is what is the speed of the dart and the cork when they're all stuck together. So after a little while here, you'll see the cork like this here. There's the dart here. They're going to be stuck together like this. And they just want to know what the speed is of this thing all stuck together. So this is the cork here. There's the sharp thing in the dart. It's stuck in the cork. And what final speed are they going to have? Okay. Kind of an interesting problem that combines a lot of different physical ideas here. Okay, so a couple things you have to get straightened out here. It is going to be a conservation momentum problem. So we are going to say P initial along the y-axis is equal to P final along the y-axis. So we are going to look at a conservation momentum between all of the motions, both the dart and the cork. But we need to know what those motions are going to be because the conservation momentum equation here, as you sort of know now, involves m's and v's. Now we have the m's. The cork is quoted to have some mass. We'll call it m sub c, mass of the cork. The dart is quoted to have some mass, m sub d, the mass of the dart. But we don't know anything about their speeds right now other than, we just don't know them. What we do know is that the dart starts at rest with 9 meters per second, and 3 meters above it is a cork, which starts at rest. So we need to sort of nail down some of those properties there. Okay. So I guess the first thing that we need to figure out is what those speeds are going to be. So we don't know what those are. But we also just need to know, when are they going to meet or when are they going to crash. So we have to do some basic kinematics to get this going. So the first thing that I'll do in particular is I'll say, well, I know where the dart's going to be at any given time. This is going to be at 1/2 times 9 times delta t squared. Where am I getting that from? This is just a kinematic equation number 1, but I'm filling in that the dart starts at the ground 0, so y0 is equal to 0. It also starts at rest, so v0, y is equal to 0. So we just have the 1/2 a delta t squared term for this dart. And there it is. I can do the same thing for the cork there. The y position of the cork starts 3 meters high, so the initial position of the cork is 3 meters high. It has no initial downward speed, it's just dropped. So we'll have a minus 1/2 g delta t squared term of the cork. So these are the positions of the two things. Now the reason why I want to know this is because I want to know where they're going to meet, where exactly they're going to collide, or alternatively, where is the dart going to be equal to the position of the cork. So I'll get this equation here, which is 1/2 9 times delta t squared is equal to 3 minus 1/2 g delta t squared, something like that. This will be the condition for trying to figure out where the dart and where the cork collide. And if I solve this thing for delta t, I get something like 0.56 seconds. So in other words, after these things are shot 9 meters per second straight up and just drop straight down, they will be collided or stuck into each other about a half a second later. About 0.56 seconds later, they will be stuck together and they will look like this. Now the reason why that time is important now, because now that I know how long it's going to take them to stick together, this is about the time the collision is going to occur. So if I just knew the speeds of the objects at this time, those are the speeds I could use in my conservation momentum equation. So I think I can find those using equation 2. In particular, I can say something like the speed of the dart now is going to be minus 9.8 times the 0.56 seconds. That's how fast the dart's going to be traveling when it collides with this is how fast the cork is going to be traveling when it collides with the dart. So it's just purely in free fall, straight down. That's the minus sign for 0.56 seconds. And also just note that v naught of the cork is equal to 0, so I don't have that term there. Likewise, I can find the speed of the dart when the collision happens. The dart's accelerating up at 9 meters per second squared, so I'm getting 9.0 times 0.56. So that gives me the speed of the dart. The two speeds that I get here, the speed of the cork is going to be something like 5.5 meters per second, and the speed of the dart is going to be something like 5.04 meters per second. So in other words, I have the two speeds now of the cork and the dart when they collide. And that's important now because those are the speeds I can use in my conservation momentum equation. So let's just go ahead and set that up. So I'm going to drop back to the key concept for this problem, which is that momentum along the y-axis is conserved. P initial y is P final y. Okay, so what do I have just before the collision happens? Well, I have a cork moving at 5.5 meters per second and a dart moving at 5.04 meters per second. So I'll do something like this. I'll say minus mass of the cork times velocity of the cork. Again, the minus sign because the cork is moving down, plus the mass of the dart times velocity of the dart, a plus sign because the dart's moving up. And what I have after they collide is I have a sort of a blob here, which is the sum of the two, mass of the cork plus mass of the dart, times, say, we'll just call it some big V final here. And that's what we want to find. That V right there is this V, which we hypothesized we wanted to find when the problem started. And so this equation will deliver it to us. So I'll just end the solution right there. You can solve this for V using your calculator. I think all the numbers are known. The problem gives you the mass of the cork, the mass of the dart. You have the two speeds. You just found them using your kinematics, the stuff up here from sort of very early in the quarter. And of course, the sum of the masses right here, because they are now stuck together as we have right here. This blob now has a total mass of mass of the cork plus mass of the dart. So they're all stuck together. So I'll leave you to solve this here, but you can certainly get V now, which will be the speed of the two things after the collision.